Hi Sejal. So you're joining for the first time?
Yes, sir.
Yeah.
Good evening.
Yeah, good evening. Can you introduce yourself?
Sir, I am Sejal Arora and I had completed my master's in physics this year itself.
Okay.
And right now I'm looking for other all the options that I have available to me, exploring just exploring the options I have.
Okay, okay. So from where did you pass your masters?
University of Delhi.
Oh, okay, okay. So you're from Delhi.
Yes, sir.
Okay, fine, fine. Okay, okay. Okay, let us wait for some time. Okay, people are joining. Plavin Kumar, you are joining for the first time.
Yeah, yes, sir.
Can you introduce yourself, please?
Yeah, myself Praveen Kumar.
Hmm.
Now I'm working at IITM as a projects associate.
Which IIT? I didn't get it.
IIT Madras.
IIT Madras. Acha. Okay.
Now I'm trying to clear grade for enrolling PhD.
Okay, okay. On which topic are you doing your project?
Uh, Using complex networks, I am analyzing the climate.
Okay, that's a climate. Okay, okay, good. So this is a simulation work,
It's like a data analysis.
data analysis. Okay, okay, good. All the best.
Thank you, sir.
Okay. Amit joined last week. Sangram, you joined last week.
No, sir.
Okay, can you? So it is the first time you are joining.
Yes, sir.
Can you please introduce yourself?
Sir, myself, Sangram Sanapati. I
Mm-hmm.
have just completed my MSc and from Revensa University, Odisha.
Which university? I didn't get you.
Revensa University,
Acha,
Odisha.
Orissa. Acha, okay.
Again.
Okay, okay, good. And anyone else who is joining? I think Shanmuga Priya, you are also joining for the first time. I didn't see you in the last week, I think.
Evening, sir. I'm Shanmupriya.
Mm-hmm.
I'm doing PhD in Manoormaniyam Sundarnad University, Tirunelveli.
You are doing masters or I didn't PhD.
PhD first year.
PhD first year.
Yes, sir.
Oh, okay, okay. So you want to still give gate. I mean, you want to change your institute.
Yes, yes.
Okay, okay, okay. Fine. Okay,
Thanks.
got it. Yeah. Okay, fine. Mm, I think we can start. People will join later. Okay. Okay. Let me share my screen now. Just 1 minute. Okay. Okay. Sandeep joined. Sandeep, you are joining for the first time, or you joined the last week or last sessions? Sandeep, can you hear me? Okay. I think okay. Okay. I will share my screen. Let us start the session. Is my screen visible?
Yes,
Can
sir.
okay, fine. Okay, whoever joined for the first time, so let me give me a short introduction of myself. So I am Birshar Roy. I am pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science. So as all of you know, in this NPTEL GATE course, we will be discussing previous year's GATE physics questions, few of them in the per session, per classes, and a little bit theory part if required. Or basically, we'll be focusing on the solution, how to solve the problem, approach to the problem. So yeah, that's it. So let us start the session today. Okay. So this is our first question. So the pattern will be I will give you some time so that you can think, you can share how you are trying to solve this problem, or if you are getting the answer you can tell me, and also I will share my solution what I have done for this. Okay. So this question is from GATE Physics paper 2020. This is a numerical answer type question having 1 mark, and this is from electromagnetic theory, specifically from electrostatics actually. So the question is, a conducting sphere of radius 1 meter is placed in air. The maximum number of electrons that can be put on the sphere to avoid electrical breakdown is about 7 into 10 to the power 9, where n is an integer. The value of n is, so you have to find the value, the interior value of n. Here you have to assume several couple of things. So first thing is, breakdown electric field strength in air is about mod of E equals to 3 times 10 to the power 6 volt per meter. Permittivity of free space, that is epsilon naught, is 8.85 multiplied with 10 to the power minus 12 farad per meter. Electronic charge, that is 1.6 times 10 to the power minus 19 coulomb, that you know. So using this information, you have to find the value of n here. So first read the question carefully and let me know if you have any doubts about the question. Is the question is clear to everyone? Any doubts?
Trying to understand, sir.
Okay, please try. If you have any difficulty in terms or anything, please ask me. We will take at least 5 minutes maximum. Then I will ask people how they are. Also, meanwhile, you can share your thoughts about the solution. How can you approach that problem? So anyone can tell me how can we deal with this problem? Anyone? Okay, no one is.
So we have just to calculate the number of electrons that would be required to produce the given electric field in that particular sphere.
Yes, so basically the maximum number of electrons to produce this breakdown electric field. That's the maximum here, right? You're correct. So how will you do that then?
So we can use the fact that a sphere behaves like as if all the electrons are placed at its center. So kq by r square would be the formula.
So wait. So why all the charges should be at the center? So, so that's why I told everyone to read the question carefully. This is a conducting sphere, not
Okay,
uniformly
okay,
charged
yes, sir.
sphere. Okay. So this is not a dielectric sphere. This is a conducting sphere. So you have to use the property of conductors.
Charges will reside only on the
Yes,
surface
exactly. So why should the charges should be on the surface only? What's the reason for conductors?
because potential should be constant inside.
Yes, conduct potential. It should be equipotential surface, right? So that's why all
Yes.
the charges will lie on the surface of a conductor. So there will be no charge at the center. Yeah. So okay, then how to do that then? I mean this property is okay, correct? Who was that? Who was the guy told this?
So Amit,
Okay, yeah. Okay, so then what to do? This is a basic electrostatics problem. So I think you have read this in your bachelor's. Yeah.
So I forgot the direct formula, but we have to start from the Gauss law, I think. Um,
Okay,
and then
here you have to know the what's the electric field near the surface of a conductor. That's very easy formula. Can anyone tell what is that? Anyone? What's the electric field due to a conductor near the surface?
By using
Sorry, I didn't get it. You can try. I mean, don't have to worry if you're wrong.
1 by 4 pi epsilon naught into Q divided by R square.
So that is for a point charge, right? That you are saying. But here it's a conducting surface, and
KQR by R cube.
sorry,
KQR by R cube.
KQ by R cube. What is K here? I didn't get.
1 by 4 pi epsilon naught.
Q R by R cube. R is the radius of the convex sphere. So that is,
Yes.
I think you are saying for the uniformly charged sphere, not the conducting sphere actually.
Okay, sorry.
So here it is
So is
convex
it
sphere. Yeah.
sigma upon 2 epsilon naught?
Sigma upon 2 epsilon naught or epsilon.
Yeah.
So what is the sigma here?
Surface charge density.
Yes. Then what will you do? Yeah, it's correct actually. This formula
So
needs to be used here.
we have been given the breakdown electrical field strength.
Right.
So that will use instead of E,
Hmm.
and we'll calculate the charge. I'm
Then
not sure.
yeah, it's correct. It's correct. Approach is correct. So how will you find it's correct what you have said. So then how will you go into the that electron density here from that formula? That's why I am asking. That formula for sure you have to use. Anyone? So if your electric field is sigma by epsilon naught, where sigma is the surface charge density. So what's the relation between surface charge density and number of electrons in that system?
Q equals to sigma dA
Sigma
or
d sigma
dA.
d. Sorry. I didn't get it.
Sigma into A means area.
Okay, yeah. So what's the area here?
4 pi R square.
Yeah,
The
that
radius.
you use that, then you will get the total charge, and then from the total, if you know the total charge, then how will you find the number of electrons? If you know the total charge from that, then from that,
Divided by the electron charge.
yes, let's do that. That will give you the number. It's not so hard. I mean, just if you know the formula and if you know how does it define the electronic charge density, surface charge density, then that's the thing. Yeah, please do that. Please do the calculation. Let me know what's the value of n. Okay, this approach is exactly correct. You can use the. I think you have to use the calculator because you may have to use the logarithm. You can use your calculator, scientific calculator for this. Okay, will I wait to get the answer?
Yes, so wait a minute.
Yeah, okay. Just take your time. Please let me know the answer value of n. And whoever has joined late, please read the question. If you have any doubt, please ask me then. If you have missed something. Let me ask other people. No one is responding. Is okay. Okay. So
Sir,
Sir, it is 2 into 10 to the 13 electrons.
13.
who is saying 13? Can you please tell your name?
So, I mean,
Okay. So okay, you are getting 13 and
someone else was saying too.
sorry,
Someone else was answering that too.
13. Okay. Okay.
No, sir, no 13. I was getting 2 into 10 to the power 13.
2 into 10 power 13. Okay.
Yeah, I
Mm,
mean, here only the power is been asked, so I'm just answering about that. Only.
I got it, got it, got it. The value of n you are getting 13. Okay. Okay, let me wait for other answers. I mean, any Sejal, did you try this question?
Yes, sir. Maybe I've gone wrong in somewhere in the calculation. I was
Okay.
supposed to get 7 into something.
Uh, yeah. Um, yeah, just do it. Okay. I'll wait for one another 1 2 minutes. People, please try and let me know.
I want to see the question.
Oh, you do. Oh, sorry, sorry. You joined late.
Yes.
Okay, just wait. Just wait. Just wait. What's happening here? Okay. Just see the question. If you have any doubt, please ask me. Someone has posted something. Just let me check. Santunath. Who is Santunath? Can you please introduce yourself? I think you are joining for the first time.
Yes, sir. I'm joining for the first time.
Yeah.
Sir, I'm Santunath from West Bengal. I
Okay.
have completed my MSc from IIT Roorkee, and
Okay.
I'm preparing for GATE NET exam for
You have
2026.
passed this year?
Hi, this year 2022.
Okay. 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 Good. Okay. So what's your answer? 14. You are saying.
Yes, sir. Answer is 14.
Okay. Okay. Anyone else? Okay. I will ask some people.
So
Okay.
15 for the
Okay.
value of n.
Okay. Harish, you are saying 15. Okay. So I got 13, 14, 15. Okay. Okay. Just hold on. Let me ask other people. Maybe Santanada, Sajul. Swati. Swati, you are joining for the first time? Okay. Mm, okay. So, okay. Okay. Fine. Someone has posted something. Can you please tell me? Robin Kumar is getting 13. Okay. So my screen is visible, right?
Yes, sir.
Okay. So the answer. Okay. I think whoever has answered has done correct. Method is correct, but the answer should lie between 14 to 15.
15, sir.
Okay, so either
15.
14 or 15. So the in the interior form your answer should be okay. You will get when I am showing the solution, then you will so then I will ask who got the 13 and how did they get. Okay.
Sir,
Okay.
I'm getting 15 now.
Okay, 15 is okay. The answer should, because the answer will come, the exact value of n will come. I mean, as a fraction, and not exactly integer, but you have to round it off. So you'll understand why. Okay, so I'll show the solution now. So I'm starting that. So you are given that a conducting sphere of radius 1 meter is placed in air. The breakdown electric field in air is your mod of E, that is 3 into 10 to the power 6 volt per meter. Epsilon value is given, that is 8.85 10 to the power 12 minus 12 farad per meter, and electronic charge, that is 1.6 times 10 to the minus 19 coulomb. Now, I have already told that electric field on the surface of conductor is given by your E equals to sigma by epsilon naught, where sigma is the charge density on the conductor. So, if n is the number of your electrons on the surface of conductor, then sigma can be written as n times E by 4 pi r square. Here n is the number of electrons, E is the electronic charge, and 4 pi r square is the area of the spherical surface. So, your electric field will be now for this spherical conductor Ne by 4 pi square epsilon, right. So, to avoid the breakdown, the maximum number of electrons that can be put on the sphere is that is given 7 into 10 to the power n, right, and corresponding breakdown electric field is given 3 into 10 to the power 6 volt per meter. Just put these values here. So, you know E value, maximum E value is 3 into 10 to the power 6 volt per meter, and n value is given in the form of 7 to the power n. E is that is 1.6 to the power minus 19, R 1 meter. So, put just all the values. Then what I have done here, so 10 to the power n equals to this will be this, right, all the terms will be on the right side. So, I am getting 10 to the power n approximately 3 into 10 to the power 14. So, you have to just take the logarithm of this. So, here I am getting 14.47. It may vary, I mean you just approximately you may get 14.57 also, I do not know. I mean some people have got 15 in the interior forms, that is also correct. So, if your answer is either 14 or 15, then it is the correct answer. So, who got the 13 and what has anything gone wrong there?
Yeah, I didn't consider the values. I just checked the powers of the 10. So there the denominator should be less, means more.
Okay, but in this thing you have to be a little bit careful, because even though you are doing correct, don't do approximation, because you are given
Okay.
you are gate. I mean in the gate you will be given the calculator, so they need the precise answer actually. Okay.
Okay. Okay, sir.
Okay. So, 14 is also correct answer, 15 is also correct answer. Okay, the range was given. I have seen the answer, that was 14 to 15. So, you can whichever you get, that is correct. Okay. So, any confusion in this solution? Any questions?
No, sir.
Okay. Can I move to the next question? Okay. Okay, fine. I think whoever solved that question got it correctly, and okay, fine. So, the answer is 14 or maybe 15 also, that does not matter here. Okay, fine. So, next question I am following to the next question. Okay, so this question is from also GATE Physics 2020 paper. This is a numerical answer type question, but 2 marks, and this is from quantum mechanics. So, this is given the radial wave function of a particle in a central potential is given by your radial wave function r as a function of position smaller is a times smaller by a times exponential of minus r by 2a, where a is the normalization constant and a is positive constant of suitable dimension. If gamma a is the most probable distance of the particle from the force center, then the value of gamma is, so you have to find the value of gamma here, so that your gamma a is the most probable distance of the particle from the force center. So, is the question is clear to everyone? First let me know. Amit, is the question is clear to you?
No, sir.
Okay. What's the problem in, I mean what's the difficulty in understanding? Can you please let me know?
I don't get it. What actually do I need to calculate?
Okay, let me make it simple. So, the question is little bit twisted here. So, the question, I mean you have done the hydrogen atom problem, right?
Yeah.
So, hydrogen atom problem is basically this is a central potential problem, because charges are nuclear, right, because electrons are moving around the nucleus acts as a central potential, it will give up a central potential to the electron, and electrons are moving in that central potential, right. So, for that you get the wave function, right, there is a radial part and azimuthal part, right. So here the same thing, they have not mentioned the hydrogen atom problem, but it is the same problem. This is a hydrogen atom problem. They have given the radial part here. Okay, so in that case, you know, right, the most probable distance, the mean distance of electron for a particular principal quantum number n equals to 1 or n equals to 2 or n equals to 3. So here that is has been asked here. So what's the most probable distance? So you have to know how to find the most probable distance for a given potential or given wave function. So uh, is it okay to understand now? I mean the
Yes,
problem
sir.
actually, yeah.
Yes, sir.
So anyone knows how to find the most probable distance if you know the radial function? Or at least whoever has done the hydrogen problem, they should know. I mean, at least it is a textbook thing how to find the most probable distance of a particle of electrons.
Sir, the calculation is we
Huh.
have to find the probability density function, that
Right.
is mod square into r square.
Mod square into r square. Yeah, it's actually 4 pi r square. It's okay. R square. Okay. That's the constant, doesn't matter. Okay. Fine. Then
So then we have two derivative over r. So we find the maximum,
where will
the
you
point
derivative
where
over r?
the most probable distance. That
Hmm.
means the if that d square into r square, if it is a peak like function, so
Mm-hmm.
at point r, there is at point r is equals to something gamma into a
Mm-hmm.
the d mod square into r square, mod of d square into r square will be maximum.
Okay.
That's why the
So
so the total factor is 0.
basically, you are trying to find the extreme point of that function, right? I mean, or either local maximum or
Yes,
local minimum, right? So
yes, yes.
basically, here it's the maximum you will get. Yeah. So that's why the first derivative should be 0 of that probability density function, right? Uh,
Yes.
okay. Fine. Please do that and let me know what will be the answer. So others got the point. I mean, what was the name? I forgot to ask. What was the name?
So my name is Santuna.
Santunat. Okay. So everyone understood what Santunat already told?
Yes, sir.
Okay. So please follow that steps and let me know what should be the answer for gamma. Take 2-3 minutes and please calculate that. Okay. Any answer from anyone? So Santunat, you got the answer?
Yes, sir. Answer is 4.
Answer is 4. Okay. Anyone else? Okay, let me ask people where they are stuck. Okay, Rituraj, you tried that problem?
Yes, sir.
So what's the answer? Did you get?
Yes,
What?
16 I am getting.
Sorry, your voice is not clear.
16, sir.
Sorry,
Maybe I have 16, sir.
16.
Yes.
Okay. How did you get
Maybe,
60?
sir, I um, first of all I find the function.
Mm-hmm.
Uh, I mod I find r square, then multiply with r square.
Mm-hmm.
It will give the complete function.
Mm-hmm.
Now I maximize it.
Mm-hmm. You made?
Maximize it by differentiating with respect
Ha.
to r and setting to 0.
Okay. Okay.
So,
Hmm. Okay. Then you got 16 from there.
yes, sir.
Just check your calculation, please.
Hmm.
16 is not correct. Priyanka, you tried?
Sir, trying.
Okay. Sajal?
Sir, I had done it without taking that 4 pi r square factor into account, so I'm redoing it now.
Okay. No. So that's the way. So basically, you have to multiply 4 pi r square or r square, whatever guys other people are saying. 4 pi doesn't matter because we will take the derivative. 4 pi is a constant. So okay. Can you say why you have to multiply the 4 pi r square to get the probability density function here? Sanjanath, can you tell why not only mod r square?
Sir, like uh, if you for in quantum mechanics,
Hmm.
we sir, let me think and tell you later. Okay, 1 minute.
Sir, I am getting 4.
Rituraj is getting 4. Okay, yeah. Please, can you
Uh,
say why? Yeah, Amit, yeah.
because
Actually,
the
angular acceleration.
probability should be normalized all over the
Probability should be normalized all over the.
space.
Yes, that's correct. So yeah, that's the actual thing. So when the total wave function should be normalized, right? So not only, I mean, yeah, the radial part also they will have a angular part. So individually the radial part should be normalized and individually angular part should be normalized. That's the condition, right? So if you want to normalize it, then you have to take the radial part, that is 4 pi r square, the surface. So that's why the 4 pi r square terms come here in the probability density function, so that you, when you will integrate over dr, the probability density, you will get 1. That's the way to do it, right? So yeah, Amit was right. That should be normalized over the surface. Uh, okay. So anyone, other people, what is getting? So someone got 3. Can see 16. Or Rituraj says 4. Rituraj again 2. Okay. So Rituraj, your final answer is 4. You are saying.
Yes, sir. 4.
Okay. Okay. Rituraj Santranath got 4. Amit, what are you getting?
Sir, I'm unable to do this. I'm sorry.
It's I mean I already told you to what to do. So basically you have to take mod r square, that is given the radial function. So that mod of that square, then multiply with that 4 pi r square. That is your probability density function. Then just take our first derivative with respect to r equals to 0. So that thing will give you a r value, small r value, right? That is your most probable distance. That's the
Oh,
thing. Anyone else has done this? Only the calculation you have to do here. 4 5 lines, I think. Swati, you have done? Praveen Kumar?
Yeah, I have
sir,
done.
two.
I'm getting the answer for.
Okay, you got 4.
Sir,
Okay,
two. I'm getting two.
Amit is getting 2. Okay. So there are confusion between 2 and 4, I think. 3, 1 got, I do, okay, there is a 2, 3, 4. I got 3 answers. Okay. So let us see what's the solution, and whatever, if that is not matching with your answer, then please understand what mistakes you have done in your solution. Okay. So let me start. So your radial wave function is here, that is given r as a function of small r, that is a times r by a exponential of minus r by 2a. So therefore, probability of finding the particle between your position r and r plus dr is given by PR dr equals to 4 pi r square mod of r square. So the r is here radial wave function. So this is the probability density function actually. So sorry, I think I have missed here dr here. So basically PR is your probability density function. Okay, so then it will give 4 pi a square divided by a square times r to the 4 exponential of minus r by a times dr. Okay, so here a is the normalization constant, a is the positive constant of suitable dimension. So can anyone say what is the a here in case of hydrogen atom? Anyone? If it is a hydrogen atom wave function, then what should be the a? What it is called? Can anyone knows this?
Board radius.
Okay, yeah, exactly. This is a Bohr radius for hydrogen atom problem. Right,
5.3 Armstrong.
right, exactly. Okay, so now to find the most probable distance r of the particle from the force center, or the value of r where the probability of finding the particle is maximum, we can say that the first derivative of the probability density function equals to 0. So just take the first derivative of your this PR, this part without dr. So this will be the dr of 4 pi a square by small square times r to the 4 exponential of minus r by e. So here 4 pi a square by square is constant, so you can take it out. So here you will get two part after doing the derivative. So you will get first is 4 r cube times this exponential part, exponential of minus r by a, and second part you will get r to the 4, just take it and do the derivative of this part. So you will get minus 1 by a times exponential of minus r by a equals to 0. Now take the common here from, you can take the common r cube exponential of minus r by a. So we will get 4 minus r by a times r cube exponential of minus r by a equals to 0. Now the other part, so this part r cube exponential of minus r by cannot be 0, because it will give r equals to either 0 or r equals to your infinity. That is not possible, right? Because r equals 0 at the nucleus, the electron cannot stay, and r infinity is basically you are going out of the atoms, or in case of hydrogen atom, right? So here you will get 4 minus r by a equals to 0. So your r equals to 4a. So given the most probable distance is gamma a, so for sure your gamma value is 4. So if the gamma is the most probable distance of the particle from the force center, then the value of gamma is 4. Okay, so I want to now I will just tell small tips or tricks to deal with this kind of problem, because you can just tell the answer by looking at the wave function for this problem. So what's the key point here? So this is a hydrogen atom problem that you understood already, right? So for a hydrogen atom problem, if the I think someone has written the formula in the comment box, I have seen. So for the H atom problem, hydrogen atom problem, if the radial part of hydrogen atom problem is proportional to exponential of minus r by n. So here n is basically your principal quantum number that you know, right? So in our case, the n is 2. So the principal quantum number for that radial wave function is 2 in our case. And if you know the principal quantum number, then it is a formula that the probability of finding the particle is maximum at r equals to n squared. So if you know the n value, then you can directly tell the maximum, your most probable value of r is n squared. So in our case, n equals to 2. So that should be r equals to 2 square a, that is 4a, right? So is the things are understandable? Yeah.
So how do we know the n is 2?
N is 2, it is given. So if you see the exponential part here it is given 2 in the question, right?
Oh yeah.
Yeah. So that's the tricks. If you know this, then you don't have to calculate all these things. That's the generalized thing. Okay. I think someone has written the more generalized formula n square a by z. If you have not a hydrogen like atom, but not the number of electron is 1, that is z, then it should be n square a by z. Who has written that thing? I am very happy that you remember that. Sandeep Kumar Yadav, yeah. So, is the things are okay with everyone? Any confusion?
Yes, yes, sir.
Okay. So, I'll just ask who got 3, Sangram Sinapati. So, what mistakes you have done?
Sir, in derivative, sir. I
In
just got
derivative, you
wrong.
did mistake actually.
Yes, sir.
Okay, okay, okay. Okay. Please try to avoid that kind of mistake because you're doing,
Sir,
you're,
in the starting we have taken derivative as a zero. That was
which derivative is, sorry,
sorry.
I didn't get.
Sir, at the starting of we
Just,
have done the
huh.
yeah.
Which one? Which one? I didn't get your point. Can you please repeat?
Yes, sir. At the starting we have
Huh,
done the dr by yeah. So as yeah zero, this dp by dr is equal to zero.
huh, yeah.
So here we how we get the probability will be a zero.
Probability will not be the 0. Your, I mean, why probability should be 0? I didn't get your point.
Sir, no. Miss the derivative of probability with respect to r will be zero. That I didn't get.
Oh, acha, acha, acha. Okay, okay, okay. So you have just, so what did you do? You, I didn't get your mistake actually. What, just trying to understand how did you go, how did thing gone wrong actually.
Yes, that's why I'm asking. Can we put that zero and we cannot do any other constant?
So you have to take the derivative equals to 0, obviously. Then other constant means?
Okay, sir. Okay, no problem. Get it.
Okay.
Because if we try to plot the means graphically, then the slope should be zero. That's why means at the minimum point and the maximum point,
Yes,
at
yes,
both points
yes.
the slope is zero.
Yes, yes, exactly. That's the extremum point you have to find. So in this case, if you do this d square dpr dr square for at r equals to 4a, then
Okay,
you
sir.
will get it is less than 0 because it will get, that means it will be maximum value, right? That's the condition.
Oh, okay, sir.
Yeah. Okay. Oh, okay. I think it is okay with everyone. So next, going to the next question. So this is a very common question. So I expect everyone can solve this. So this is the question from GATE Physics paper 2020. This is a numerical answer type question having 2 marks. This is from quantum mechanics. So the question is, a free particle of mass capital M is located in a 3-dimensional cubic potential well with impenetrable walls. So you have to find the degeneracy of the 5th excited state of the particle. Okay. So the question is pretty simple. I think it is understandable to everyone. Any confusion? Please ask me then. Is the question is clear to everyone? Any confusion to anyone? Please ask me. So Amit, is the question is clear to you?
Yes, sir. Yes, sir.
Okay. Can you solve this?
Yes.
Okay. Please take your time and let me know. I will expect more answer from more people because this is a basic quantum mechanics problem. So what is the formula for energy in 3-dimensional quantum well? Can anyone say?
nx square plus ny square plus nz square.
Sorry, your voice is not clear. Can you please tell again? Hello.
So nx square plus ny square plus nz square
Huh.
ht square upon 2ma square, where a is the length of a cube.
Okay. Pi square h cut square, right? Or
Yes, sir. Yes.
pi square. Okay. Yeah, that's correct. So basically, there will be 3 quantum numbers because you have 3-dimensional problem, right? Okay, someone has written. Let me see. Okay, please. That's the only formula you have to use to find the answer. Now you have to find the fifth excited state for this problem. You have to find the degeneracy. So someone is saying degeneracy is 6. Okay, let me check with others. So who said that formula? I forgot to ask the name actually. Sangram. Okay. So Rituraj, you're doing that? Am I audible? Am I audible to everyone? Can
Yes.
Yes, sir.
okay,
Yes, sir.
okay. So okay, just take 2 minutes, I think. Okay, let me ask one by one then. So basically, the formula everyone understood, right? What you have to use here? Any
Yes,
anyone?
we have to just check for the values of nx square plus ny square plus nz square and arrange them accordingly.
Ha. So basically, you have to find the combination of nx, ny, nz for the fifth exercise state. So how many combinations are possible? That will be your answer, right? That is the DJSC, because for all that state of nx and ny, nz, you are getting the exactly same energy for the fifth exercise state. So okay, let me ask one by one. So for ground state, what will be the nx, ny, and z value? Can anyone say?
111.
111.
111. So any other combination is not possible, right? Only this is possible. So your degeneracy is for ground state, it is
1.
1. Okay. Then for the second, first exercise state or the second state,
1 to 1 or
so how
any,
many
1 1.
any
how many
combination.
combinations is possible?
3.
3. So degeneracy is 3, right?
Yes.
Okay. For then next second excited state,
1 2 2.
3.
sorry, who said 1 3 and who said 1 2? I didn't.
I said 1 2 2.
1 2 Amit.
Yes, sir.
And who said 1 3? Okay. So 1 2 2 will be the second, because if you choose 3, so then it will be
9.
greater than that energy, right?
Yes.
Understood?
Yes.
Yeah. So how many combinations possible, Amit, for 1 2 2?
3,
3.
sir.
3. So basically your second excited state will have degeneracy 3, right?
3.
So okay, this was second. So for third,
The 113.
1
so
3
there will be
degenerate.
1 1 3 or 1 3 1 or 1 3 1 1. So that is also you will have 3 degeneracy of 3. Okay. For fourth excited state, sorry,
2 2.
so this will be your fourth excited state. Yeah. Fourth, so 2 to 2. Yeah. Right. So only one possibility is there, right? So 1, there will be degeneracy. And for fifth excited state, you will have
3. 2 2 3.
2
So
to
it will
3.
be 3.
312.
1, 2, 3, sir.
Oh, yes, 1 2 3.
So 1 2
Sorry.
3, you will have how much
6
possible?
degeneracy.
Okay.
6.
So I discussed lots of things. So it instead of fifth exercise, you have been asked fourth exercise. So basically, you understood, right? What you have to do in this case. I will obviously share the solution. what is the exact method to go to the final answer. So that's why I discussed every excited state, degeneracy of every excited state. Okay. So answer is obviously 6, that is correct. So let me just formally discuss the solution now. Okay, just go to the solution part. Okay, so the energy spectrum of a particle in a 3-dimensional cubic potential well of side L is E with a subscript, that is nx, ny, nz, that is the quantum principal, that is principal quantum number of this quantum problem, that is given by pi square h square by 2 ml square times nx square plus ny square plus nz square. So here I have put this constant, this is pi square square, this is as alpha, and p is sum of this nx square plus ny square plus nz square. So basically your energy will be alpha times p. And here nx, ny, nz can take any integer values, that 1, 2, 3, 4 and so on. So let us see energy configuration for a free particle in 3-dimensional quantum cubic potential well with impenetrable walls. Okay. So we will start one by one, first from the ground state. So just check the list here I have written. So for the combination nx, ny, nz, your ground state will be 1, 1, 1, because minimum value of nx, ny, nz is 1. So that will be your ground state. So here p value is 3 because p is nx square plus ny square plus nz square. So your energy value for this will be 3 alpha and degeneracy is 1. And for first excited state it will be 2, 1, 1, because this is the second most minimum value here, right. So after this you will get p value is 6 for this combination, and here 3 combinations, 3 sets of nx and nz will give this value of p is 6. So your E2 value is 6 alpha here. So this is a first excited state energy. So here degeneracy is 3. Similarly, you will get for second excited state, you will get 221 or 212 or 122. So your p value will be here 9 and your energy value will be 9 alpha. Here also degeneracy is 3, and for the third excited state it will be 113 or 131 or 311. So your p value is 11 and your energy value is 11 alpha. So it is here also degeneracy is 3 for the third excited state. But for the fourth excited state, you will get only the combination 2, 2, 2, and p value is 12 and energy value is 12 alpha, and degeneracy is 1. And for the fifth excited state, you will get this combination of nx, ny, nz like 1, 2, 3, 2, 1, 3, 2, 3, 1. Basically, you have to rearrange, you have to just rearrange the 1, 2, 3 here. So you will get 6 combinations, and you will get p value equals to 14 and E6. And this is the energy for fifth excited state, that is 14 alpha. So here your degeneracy is 6. So fifth excited state particle has the energy E6 equals to 14 alpha, that is 14 pi square h square by 2 ml square. And the possible sets of quantum numbers nx, ny, nz is this 6, 1, 2, 3, 2, 1, 3, 2, 3, 1, 1, 3, 2, 3, 1, 2 or 3, 2, 3, 2, 1. So degeneracy of the fifth excited state is 6. Okay. So is the solution is okay with everyone?
Yes, sir.
Any confusion with anyone? Please let me know. So, okay. So, Sandeep, you wrote degeneracy is 1, 2, 2, 2, right? Sandeep, or who was that? Sandeep Kumar Yadav. Okay. So, I think you have mistaken in that. You have chosen the fourth excited state. That's why. Okay. Anything else? Okay. Please ask me if you have questions. And this this was my last question for this session. Just let me know. Just wait. Okay. Okay. Then thank you guys. Just stop present. Okay. Okay. So any questions, guys?
So,
Yeah.
I have a question. So, how did you got into IISc?
How did I get into? Okay. So I cracked GATE, JEST, and net that time. So basically mode of entry were all the three. You can apply through your rank. Okay, I applied through Get and Jest, and the mode. I mean, they will choose only one mode of entry, in which your rank is greater. I mean, lesser, right? That's the good rank. So my Jest rank was better than Get rank, so I was selected through Jest. But after that, I got PMRF, Prime Minister Research Fellowship. After, I mean, I applied after joining here.
Okay, sir. And how to get this PMRF?
So now there are two things. So one, though, you can directly apply after MSc, and you will be. I mean, there is some criteria. I think I forgot. At our time it was. I mean, there is a two channel actually, direct entry channel and lateral entry channel. So in case of direct entry channel, people usually apply after MSc, Masters or BTech. So in that case, I think the criteria is your CPI. You have to have CPI greater than 8, minimum 8 CPI, CGPA, and I
I
think
think minimum minimum is 8.2. I think.
8.2.
Yeah.
At our time it was 8.5. I know, but after that it was changed. I think at our time it was 8.5. Okay, and because rules has changed, I mean, I got it 3 years back. Okay, so now lots of thing has changed. So you have to check the portal for PMRF. So at our time there was no lateral entry channel. So lateral entry channel is basically when you will be in an institute which is PMRF granted, then you can apply through the institute only. So that option was not in our time. We have to apply. We have to go through that direct entry channel. We have to apply it through the fresh as a fresh student. And if you are lucky, then I mean you have to give the interview. And if you are lucky, then you will get the same institute. Otherwise, you have to change your institute if you want to opt the PMRA. But now it became easy because if you are in ISC or any IITs, then you can apply through that institute. If you get the fellowship, then you will be in that same institute. That is the lateral entry channel. Okay.
So for direct entry, it doesn't matter from which college or university or institute we are coming from.
I think it doesn't matter. I have to check. Please check the PMRF portal. I forgot. Okay, I mean
Okay,
this
sir.
was 3 years back. I mean when I applied for this. So please look into the portal. There is a nice portal of PMRF. Please check that the criteria. There are lots of criteria, criteria. Please check that. You have to write a research proposal and other stuffs you have to do for that.
Okay, sir.
Okay. Any questions again?
So, what is the desired rank for getting into ISC in GATE and NET and West?
It actually varies. I can tell what was in our time. I think they will call up to in our time. I think up to 200 they called. I didn't remember exactly, but at least 150 200 depends. It varies actually. Okay, but up to I think 150 200 they will call for interview.
Okay, sir.
Okay. Yeah. Any questions? Okay, how to choose a field in PhD? Okay, so it actually little bit tricky question for me because I mean, if you have done any project work in your masters, then it will be easy to choose or ignore that field because you will understand that the field is suitable for you or not, right? So in my case, I was working in my masters. I work in condensed matter physics, and I like that. That's why I chose that field. And in PhD, you have to choose a specific project in that field. So that too, you have to visit the professors and you have to ask what projects are available. Then you can choose which projects you like and which topic you like in that condensed matter. I mean that I have done in my case. So if you have not done any project or you are not serious in master's project, then you have to do some research, like research article you have to see, and you have to look into that, what topics are in what topics people are working, what's the hot topic. That will be, I think, good to choose, and that is very, that field will be explorable to us, and there will be much exposure actually.
So,
Yeah.
what if I don't want to continue with what I've done, means
Hey,
in my
that's
project?
that's fine. That's fine. That's what I told now. I mean, if you don't like, then you have to look into the other field, obviously. So for that, I mean, you have to just know little bit about the field, right? Otherwise, how will you choose? So you have to just do
Yes.
some have some knowledge what work is going on in that field, and what makes you interested in that field. That you have to find. That depends on you, obviously. That there is no hardcore rules to follow, what field to choose. You can, I mean, you have to just see what work is going on in that institute, what professors are doing, in the group of professor is doing. Then you can just see what makes you interested. That's the thing.
Sir, it depends only on IITs. They can provide the PMRF. Is they will not provide?
I think not only IITs, there are almost 50 institute now. Not only IITs. I think there are JNU also now.
Hyderabad also.
There are lots of institutes have been included. I mean, in our time, there's only IITs and NITs. I remember that, and IST obviously.
Sir, who is from the NIT? Will they get the
Yeah.
PMRF?
I think NIT is under I mean, they are considered as a pre-med granted institute. NIT.
But sir, in the page it is not showing for NIT.
NIT is not showing.
Yes,
Okay,
sir, but IIT is
just let me give me 1 minute. I will check now.
okay, sir.
Hmm. Just give me 1 minute. So can you hear me?
Yes, sir, I
Yeah,
can hear.
so I can see here lots of institutes have included, like BHU. BHU is actually IIT, obviously. So I see IZAR. Oh, IZARs are there actually. Then IIT, all the IITs, IIT BHU and Varanasi Hindu University is also there. So that is same, right? BHU and IIT BHU. I don't know why.
Yes,
Uh, okay, IIT is there. All the IITs are there. I can see, and see here it is written in NIT, in National Institute of Technology. Tiruchirappalli is there only, I
sir,
think.
sir, only one it is there.
Oh, I think it's not included. I think it will be included soon. I don't know how they decide this, which NIT will be included.
Sir, that is showing only they can get the
Yes,
PMRF.
so I mean, if you have been already admitted to that institute, okay, then you have to apply. If and you have to, if you want to be in that same institute, if your institute is in PMR granted, then why
Yes,
will you change your institute, right?
yes.
And if you don't, if you want to get PMR, if you don't consider that what will be my institute, then you have to apply for the fresh direct entry mode. So, I mean,
Okay,
what I am trying to say, if you are in a PMF granted institute as a regular fellow, then you can apply, then you should apply through the lateral entry channel. But if you are in an institute and you don't like to be in the institute, if you get the PMRF, then you apply as a fresh student. That's the thing I am saying.
yeah, okay, sir.
Okay, so there are also University of Hyderabad, Aligarh Muslim University, I can say University of Delhi is also included here now. So, yeah. Uh, okay, so any
So, what is the topic of your research?
my topic of research is I am working on graphene plasmonic devices, and basically my measurmental technique is this is called Johnson noise. I don't know you have heard about that. That is called thermal noise or Johnson noise. So I can tell you briefly what is that. So that is basically Johnson noise is a electronic invasive technique to probe a temperature of a sample. So I mean, your when you are, I mean, I have to say, if you have a system, you are heating it up, right? So you need a thermometer to measure the temperature, right? So for that you have to touch the sample, right? But I mean, the technique Johnson which is used, that is the electronic technique. You don't have to go into that sample. That will measure some electronic signal, and that will directly tell you what is the electronic temperature in that sample. So what happened when you excites a sample by optically? So my work based on plasmonic device is basically optically excited sample. So devices. So in that case, we shine the device or sample by optical illumination. So what happens? Electrons will absorb that light and it will get heat up. But people because we don't have the provision to go into that sample and will measure directly the electronic temperature directly. It's not so easy. So we don't have to go into the sample, we directly measure the electronic signal, and from that there are some formulas and everything theory, we can tell the electronic temperature, what is the exact electronic temperature in that system when you are exciting the system. So this is a very old method, but it is very challenging to develop the because it is very sensitive. Okay, because when your thermal fluctuation will be there, the voltage developed will be of the order picovolt or nanovolt. So it is very hard. You need very sensitive setup to measure that voltage accurately. Uh, I mean, I think I could explain. I mean, it is understandable.
Yes, sir. Sir, if
Yes,
Yes.
sir. Yes.
sir, if sample is far from the sensor, so
Okay.
it will the sensor, yeah, will the intensity matter of that sample? Because if it is emitting the intensity of any photon anything, then
Okay.
will it catch that? Okay,
I mean,
yes,
you are saying that what's your question? So basically, if your sample is far away from the source, optical
yes,
source,
yes, sir. From
it
sensor,
from sensor means where that sensor that is measuring the temperature.
yes, sir.
Okay, so that's the beauty of this Johnson noise technique. It doesn't matter actually.
Oh, okay.
That's the beauty of this. So the sensor doesn't matter. I mean, if you want, I can show you the schematic if you are interested. How it
Yes, sir.
looks like.
Yeah, I'm also studying in semiconductor.
Okay, okay. I
Yes,
can
sir.
I can show the only schematic of the setup, not the exact setup now. I don't have the exact picture of the setup with me now. Okay, just wait for hold for 10 seconds. I will open the PPT. Okay.
And so, which optical wavelength is being used to heat up the sample?
It depends how, at which you are getting the resonance. So you know plasmonics little bit, right? I mean plasma you know plasma resonance, right? You have
Not really,
not
sir.
well. Okay, okay, okay. I can discuss for 10 minutes, not more than that, because it is already up to some. Okay, just give me give me 1 minute. I have to open the PPT. Okay, just wait.
And so this Johnson noise technique uses an approximation.
No, it's not approximated. It's a very small formula, but it's very accurate. I mean, I'll show you.
Okay.
Just wait. Give me 1 minute. I'll show you. Just 1 minute. I have to open the proper PPT. Okay. Okay. Fine. So okay, I'm sharing the screen. Just whoever is interested, please check this. Is my screen visible? Just wait. Is my screen visible?
Yes, sir.
Just wait.
Yes, sir.
Okay. So you can see the setup schematic, right? The left one, left topmost left. Can you say
Yes,
Yes,
yes?
sir.
So see here, why someone was asking about the distance of the sensor. So basically, this is a electronic arrangement, right? So this is basically connected to the sample. The two leads are connected to a sample. Here one lead, here one chrome gold contact we use. So it doesn't matter. I mean, you just need the two contacts over the sample, and that will measure your electronic signal, that will convert your temperature. I mean, you will know the temperature. But I think I should not discuss this because it's a very long story. I have to tell everything then. So this is a setup look like actually. There are lots of electronic components you need. So this is the beauty. Using electronic technique, electronics. You are measuring the local electronic temperature of the sample. So basically, someone asking the about the just okay. I can show you the Johnson noise formula for this. Just wait. Oh, I think in this it is not there. Just wait. Just give me a second. I have to I forgot in which PPT it is there. Okay. Okay, I found that. Is my screen visible? My screen is
Yes,
visible?
sir.
Yes.
Yes,
Yes,
sir.
sir.
So this is the working formula we use usually. Okay, this is a very simple formula. So I can explain little bit here, not everything. So basically what happens, so photons are basically, black body radiation formula, right? So what happens in your sample, so forget about the optics. So just consider a conductor. Okay, so there are electrons are getting scattered with everyone. So okay, so what happens, the local temperatures are maybe different because some electrons may have greater energy, some electrons may have lower energy, right? And after scattering it will lose energy. So what happens, there will be a thermal gradient in the sample, and that thermal gradient is called thermal noise actually, because this is very energy fluctuation. There will be energy fluctuation, right? Because energy of the every electron will not be same, and it will vary randomly because of the scattering. You understood, right?
Yes.
Yeah, so because of the fluctuation there will be a voltage drop. Okay, because there will be a potential changes in the sample, but this is very small. You cannot measure that with a usual voltmeter. This will be observed picovolt or femtovolt also, whereas it's 10 to the minus 12 volt. So you cannot measure that usual. So that voltage fluctuation comes due to the thermal fluctuation, because the electronic temperature is not constant all over the sample, and that is given, that is related, and obviously thermal power is related to a thermal photon, and that follows the black body radiation formula. So this is the quantum formula. But when you are choosing the frequency range, because you have a EM, that is a EM radiation, thermal radiation is a EM radiation. If you are choosing the range such that your HF by kBT is very small, right? So right, your frequency range is maybe megahertz, and your thermal energy is, I mean, at room temperature it is 20, what is that, 25 milliliter volt, right? And if you see, the frequency will be much larger than megahertz. So then you can approximate this formula up to so this approximate formula is known as Johnson noise formula. So JB Johnson first introduced this concept. So how can we use the electronics to measure the electron's temperature in a sample? So you can see here, if you measure that mean voltage square, and if you know the resistance of the sample, and if you know in which frequency range you are measuring the bandwidth, then you can directly tell the temperature of the sample, the electronic temperature of the sample. Is it clear? I mean,
Yes, sir.
Yes, sir.
so this is the,
So, but
yeah.
so, but you have said that we don't need any actual contact, but in the schematic diagram where you have shown, there is contact, means at 2 points.
When did I say that you don't need any contacts? For electronics, obviously you need contacts. Otherwise,
Okay, okay, okay.
so that's the thing, na? I mean, for thermometer, you have to touch the sample. I am not directly touching the sample. I am just lithographically drawn to contacts from the sample, and from there I have made the contacts. So it is not directly touching to the sample. So you are not destroying your sample, basically. What I mean to say.
Okay, okay.
Although one more thing is, the sample size is very small, because I am working on graphene, right? Graphene flake size is 40-50 micron. You cannot see that sample with a bare eyes, so you cannot take a thermometer and go to that sample, right? If it's not a bulk sample.
Yes.
Yeah.
So have you used JFET MOSFET in triac also device in semiconductor?
I am not
Like,
working on semiconductors, so sorry, I
so
am.
no, but
Yeah.
in sensor we need to work with the it's just like FET devices.
Here in this case I am not using it. I don't need to use that,
Oh,
because
oh,
in this case I think, yeah, so I already shown the schematic, right? Yeah, just let me go to the schematic here. Okay, Where is the schematic? I forgot. Okay, so you can see here there is a low noise amplifier is there, a mixture is there, low pass filter, a Schottky diode. That's the semiconducting device you have to use. That's it. This is the case.
Yes. Okay.
Yeah. And I mean, why I said that is not so easy, because lots of calibration needs to be done to get the sensitivity, proper sensitivity. So there's a challenging thing here.
Yes.
So yeah, okay. I
Thank you
think
very much, sir.
okay.
Thank you, sir.
Thank you everyone.
So
Oh,
the application is just in being able to measure the temperature of the samples, or is spans beyond that as well?
basically it measures the noise. Okay, not only temperature. From noise value, no, I mean from that noise signal, we can measure the temperature. And in my case, I am using the temperature. Yeah, mostly it calculates the temperature. Actually, Johnson noise is to measure the temperature. Actually, I don't know how can we use other things. I mean, how can we get other things from this? I have to check. Mostly people use Johnson noise to measure the temperature. Actually, that I
So
that
surrounding noise can affect that, no? So noise.
surrounding noise. So that's the thing. There are three regime of noise. So if in physics there are three types of noise. Okay, one is low noise, that is 1 by f noise. You may have heard this, right? Pink noise or flicker noise is called. That is called. So that comes in the region kilohertz, and thermal noise is in the megahertz. Okay, and there is beyond that there is short noise. So other noise will not interfere because the frequency range is different.
Okay, sir.
Okay, okay, fine. Thank you guys. So one more thing, actually, I am uploading these videos, not the live sessions in my YouTube channel, only the solution part. You may please visit. I can share the link if you want. Please visit that. Whoever is new, just give me few seconds. I will share the link. Please subscribe to that. It will be helpful for us to grow our channel. Okay. It is very slow. Okay.